Hello everyone, welcome back to our course in herbal drug technology. If we recollect, in the previous session we have seen standardization. We saw different types of standardization: physical, chemical, biological, but most importantly we said that since phytochemicals can be estimated using chemical methods and phytochemicals are responsible for the pharmacological activity, thereafter we will see what are called as the chemical method of analysis. In your previous session we already saw the standardization of an important herb which is used in cough, and that's your adulsa. Today we see a standardization of a drug that is a common ingredient of an Ayurvedic churna, the famous churna Triphala churna, and that drug is Haritaki, or often referred to as your Terminalia chebula. In this particular session we will be dealing with standardization using UV-Vis spectroscopic as well as chromatographic methods for determination of different chemical compounds present in Harda, Haritaki, or often referred to as your Terminalia chebula. So what is this drug? So Terminalia chebula, often referred to as chebulic myrobalan, Harde or Haritaki, is an ingredient of Triphala, which are three fruits, principally Harda, Behda and Amla. Of that, Harda comes from this Harde fruit, which is actually obtained from the dried ripe fruits of Terminalia chebula, which is a Compraticeae family member. Now this is a plant which is commonly found in your North India, Madhya Pradesh, and also cultivated nowadays in Maharashtra and Gujarat. It's also found in Myanmar and Sri Lanka. Usually post monsoon you will see that these plants develop a little fruits, and depending upon that you have the tiny versions, we call it as Balharidra, as well as the bigger versions. So they are often sold as pieces per kg, and depending upon how many number of sides these fruits carry, so you can see here they are ridges to these fruits. So in market, when you're dealing with an entire sample of raw Haritaki, you can see how many sides it has. Usually between 3 to 7 sides are the ones which are there in market. If you take the Bal Haridra, which is still more rich in tannins, it's mostly globose in nature. These are collected, dried in shade, but are very rich source of tannins. So if you go to see in terms of chemical composition, it is a tannin rich drug containing about 30% of its weight by hydrolyzable tannins, which include your gallitannins as well as elagitannins. So gallitannins are the ones which are derivatives of gallic acid. Elagitannins are the derivatives of what is called as hexahydroxydiphennic acid derivatives. So you have your chebulagic, chebulinic, galloyl glucose, free tannic acid as well as free gallic and elagic acids. So what are these tannic acids? So if you see, principally when I am dealing with gallic acid is a very simple compound. It is nothing but a trihydroxybenzoic acid. Now when two such molecules of gallic acid join together and condense to form a lactone, you call it as your elagic acid. So it contains gallic acid, dimer of gallic acid, which is your elagic acid. Now what happens is, during the dimerization stage, sometimes these rings open up and you get what is called as chebulic acid. So chebulic acid is actually a derivative of elagic acid structurally. So if you see gallic acid in its dimeric form, I'll just put it next to chebulic so that you all can correlate. So this is a diphenyl moiety. This is the carboxylic end, and this opposite to that we have 3 hydroxys. Similarly, you can have this as your carboxylic end, and opposite you have a para and 2 meta-hydroxys. Now what happens is this hydroxy is often lactonized to give you what is called as your ellagic acid derivatives. So this is how your ellagic acid appears. Now if you see this structure, your cebulinic acid is very close to this. Only thing is this has opened up again to form a COOH, and here this has opened up here to form a di-COOH. So this is just a open form of ellagic acid, and that is your cebulic acid. Whereas if you see your cebulinic acid, now cebulinic acid is again a sugar in between, then you have 3 molecules of this. So you have 1, 2, 3 gallic acid and 1 of cebulic acid which has gone here. So you can carefully see both of this carboxylic acids are here, which have been involved. So cebulinic acid is 3 gallic acid plus 1 cebulic acid attached to your glucose. Now you go to cebulagic acid. Now cebulagic acid is again a sugar in center. Then again you can correlate. This is your gallic acid. And then next to you have open form here. Again you can recollect, this is your cebulic acid. And this part is an open ellagic acid. We call it as hexahydroxy. I am just putting it hexahydroxy diphenic acid. So you have 1 gallic acid, 1 cebulic acid and 1 ellagic acid in open form, which is referred to as hexahydroxy diphenic acid, all attached to the sugar. So these are the main components of your harida. Apart from that, you have other compounds, especially anthraquinones, which are present in the seeds. Now fruits that are there in market are inclusive of seeds. So what happens is whenever you grind them into fine powder, especially for preparing your Triphala churna, this anthraquinones also make their way through, and as a result the anthraquinones are also seen, but in a very small quantity. Now if you see the standardized extracts of harda in market, they are very high in tannin content, so much so that they contain almost 40 to 45% of the tannin content. So now in order to assure the quality of this, in order to standardize this, we will have to quantitatively determine these tannins. So how are tannins determined quantitatively? Again, you can do it using non-specific methods as well as specific methods. So here are a few formulations in which you can use as a sample. So say for example, I have to do analysis of tannins in Triphala churna, or specifically Haritaki sample or Haritaki powder, ya fir avleha, which is more like your Chavanprash. So all these are different matrix. Now if I have to do a quantitative analysis, there are 2 ways in which I can do this. So this quantification can be done by a non-specific method. Non-specific methods are the methods they are going to do a blanket analysis of all the tannins. So this non-specific methods include your hemolyzed blood method, bovine serum albumin method, animal hide powder method, as well as total phenol content method using Folin-Ciocalteu. So what are these methods? So we know one property of tannins, and that tannin has the ability to bind to protein, and that is the specific reason why tannins often tan our skin. So our skin has numerous amino acids, proteins. Your tannins bind to this or even animal hide. In presence of mordant, they produce deep colors. Now what if these proteins are replaced by a very small molecular weight protein such as your bovine serum albumin? Now bovine serum albumin disperses in water, and as a result you can prepare a solution of bovine serum albumin, say 100 microgram per ml, and quantify it. I can do any of the protein estimation method. I will come to know how much protein is present in my solution. Now I treat it with something like a tannin rich solution. Imagine your tea. So to this albumin solution, when I pour my tea tannins are going to react with albumin and precipitate it. So my albumin, which was earlier water soluble, is not going to be soluble, and the quantity of tannins present more will be the quantity of the precipitate being formed. So I will allow that precipitate to be formed, I will centrifuge it, and then I will check how much amount of especially your albumin is present in the supernatant. Say initially it was 100 microgram per ml, but now after reacting with tannins, my content has fallen down to 80 microgram per ml. That difference I can just multiply by the factor, and I will come to know how much amount of tannins was present. Same applies to your animal hide powder, which can also be used for the source of protein. Now the fourth method is little more non-specific, and that applies to all the polyphenolic. So first three methods applied, but they were little tedious. The fourth method is much simpler, easier, but only limitation that it has is it reacts with all polyphenolics. So this includes tannins, flavonoids, as well as other polyphenols which are present in your plant. So what is this Folin-Ciocalteu method? So Folin-Ciocalteu method is basically a mixture of reagent that is referred to as your Folin-Ciocalteu reagent, which contains your phosphomolybdic and phosphotungstic acids. Now this phosphomolybdic acids and phosphotungstic acid has your molybdenum in a complex form. So what happens is when you react your polyphenols, say for example gallic acid in this case, with a molybdenum, these are antioxidants, so they themselves will get oxidized and they will reduce. So your molybdenum gets reduced, and what happens in the process is, because they form complexes with phosphomolybdate and phosphotungstate, now initially your gallic acid, which was showing a UV maxima at 265 nanometers, the complex with metals or the presence of metal chelates here have shifted, we call it as a bathochromic shift, my UV maximum from 265 to a visible region. We saw in the previous session that visible region is very good for quantification because it's mostly a flat line. So very few compounds absorb in that range. So even if it is a polyherbal formulation, if I take my, or if I am able to convert my phytoconstituent into a colored compound, I increase my specificity of determination. So here my polyphenols will chelate the molybdenum, which is present in phosphomolybdic acid, form a bluish color complex, which will give you a absorbance at 750 nanometers. Now this complex is preferably formed in alkaline pH. The reason is we want all of this hydroxys to get ionized, to get O-. Only then it forms a better complex. So it forms a more better stable complex. So you take your tannin mixture or tannin extract of harda, which is often prepared by boiling your harda sample in hydroalcoholic 50% water, 50% alcoholic solution, and then once you reflux it, cool it, filter it, extract it one more time so that all the tannins come in. Now once you do it, you are going to take this solution, make up the volume to 100 ml, ml of it you are going to use for quantification, and that ml of it you are going to first basify, okay, and then react with Folin-Ciocalteu reagent. Now you will see a color development requires a little time. So meanwhile the solution is kept in dark to kind of rule out any reactions happening in presence of light, and then you remove it and kind of you see the UV max. This UV max is coming around 750 nanometers, which can also be used for quantification. So you can do the same thing. You can use standard amount of gallic acid, say 20, 40, 60 microgram, 80. And then you can see absorbance reading like 0.1, 0.2 and so on. Then you can plot a graph. So I am just rapidly putting it as 0.4, 0.81. And then once I have my graph, whenever I am plotting my unknown, I can automatically get my concentration. So this is how I determine very easily my total polyphenol content and tannins inclusive of it. Now I can go to a more specific method, like I said, and this specific method includes your chromatographic method such as your HPTLC and HPLC. So HPTLC, we saw that we need to take the sample, specifically extract it in a organic or a solvent in which your compound of interest is more soluble. Here, since it contains large molecular weight, we can use hydroalcoholic solutions as well as aqueous solutions. But aqueous solutions take little longer to dry and they often smudge the TLC plate, and as a result hydroalcoholic solutions here are preferred. So we will boil our drug through a form of hydroalcoholic solution, and that solution we'll use on a sample applicator, which is nothing but like a inkjet printer which is going to print your bands on this. And then what happens is, we saw you can run the sample in a development chamber. You will see all the molecules in the plants going or moving by their retention factor. So once that is done, you do a densitometric scan and thereafter you can quantify it. So just showing you an example here. So this is a TLC, especially an HPTLC of Terminalia chebula, which is nothing but your Harda fruits, which have been developed using a mobile phase, which is your toluene ethyl acetate, formic acid, methanol in a ratio 3:0.8:0.7. Now this is a method given by Indian Herbal Pharmacopoeia 2002, and you can just quantify it underivatized. Underivatized, why? Because if you see this plate is already coated with silica gel, and silica gel GF means it has a fluorescent indicator which kind of fluoresces at 254. Now your tannins being organic molecules, what happens is organic molecules do not allow the fluorescence to reach our eyes. They kind of absorb it. So when these molecules absorb it, the fluorescence never reaches the eyes or sensor, and as a result that appears like a black spot. We call it as quenching. So most of the organic molecules quench the fluorescence of your plate, and as a result can be seen very easily. So you can see in different lanes here in this paper, they have done extraction by like conventional extraction, microwave extraction, or even ultrasound extraction and so on. So they have compared, and to quantify which one is better, they have used here ellagic acid standard. This other compound which is very dark is gallic acid. So both gallic acid and ellagic acid can be used as markers of Haritaki. Okay. So in the end, when you scan it densitometrically, you will get the quantity of your ellagic acid being there. So you can see here, this is like a typical standard curve. So you put different concentrations. So you can see here track number 1 has ellagic acid 50 nanograms, 125 nanograms, 200 nanograms, 250 nanograms, 300 nanograms, 400 nanograms. So that is increasing in concentration. From there on, you can see the next compound, that is your gallic acid, which I was talking about. Both gallic acid and ellagic acid are used for standardization of your Harda. So again, gallic acid, they prepared a standard curve. You can see gallic acid 20 microgram, 50 microgram, 100 nanogram. Then you have your 150 microgram. Then you have your 200 microgram, 250 microgram. So most of them are in microgram. So here what happens is, you have again your standard curve, and now once you have your standard curve of ellagic acid, standard curve of gallic acid, you know that their area under curve is going to go on increasing as the concentration increases. You can even visibly see their density is increasing. So their intensity of peak will also increase as the concentration increase, and what happens is overall area under curve will also increase with concentration. Now you have different concentrations of extract being applied here. So you can see here the extract 1, which is like 1000 microgram, 2000 microgram, 1500 microgram, 2000 microgram and so on. So different extracts have been applied in different concentrations. Now when you extrapolate it on the concentration versus area under curve graph, you can automatically get what is the concentration of your ellagic acid as well as gallic acid in the graph. So this is done by scanning, and the scanning is being done at about 250 nanometers, but you can also do it at varying nanometers from 200 to 400. Now moving on to the next one, you can also do a standardization of your Haritaki using a simple HPLC method. In the previous session, we saw often TLC is done or run as a normal phase, whereas HPLC, most of the herbal extracts you will see, is often run or developed as reverse phase. So here also the authors have used a reverse phase C18 silica column, which is about 5 micron particle size, a flow rate of 1 ml per minute, as well as detector at 280 nanometers. The mobile phase has to be polar here. So mobile phase is methanol, acetic acid and deionized water in a ratio 15:5:80 totals to your 100. So when they did this, they got a good peak of your ellagic acid here at about 6.8, 6.739 more specifically minutes. Now in another way where they have used the same HPLC method, for this time not only just the plain harda, they have used Triphala churna. So they have used 3 standards here. You can see gallic acid, you used your chebulagic acid and chebulinic acid. So they have run 3 standards. They first standardized your Terminalia chebula extract, and they saw that you have your gallic acid, you have your chebulagic and chebulinic acid here. Or when you see your Triphala churna, in Triphala churna you have harda, beheda, amla. You know amla is much richer source of gallic acid, and as compared to just Terminalia chebula harda, your Triphala churna is much higher in your gallic acid content, but in addition to that it also contains your chebulagic and chebulinic acid. So you can determine again area under curve of each of this, and that can help you in quantification and standardization of extracts. The mobile phase here is slightly different from that obtained previously. So here are a few more references if you wish to read more about standardization of your harda extracts. In market nowadays you have tannin rich extracts to the extent of 70% polyphenol content. So yes, all these methods are going to help you standardize and recheck whether a company claiming 70% standardized extract is actually giving you 70% or it's much lesser. So here are a few references that can help you with the methods for the same, and thank you everyone for your patient listening.